blackboard, is there? Well, I can make do without one, but you may find me waving my hands and trying to draw something. Is it possible to get a whiteboard with some pens?
Yeah, I think I'll ask real quick.
Great. Okay, that'll make it easier later on. So anyway, I thought we could begin by I will just sort of silently walk through the slides that I was using this morning, and you may have some questions or things you would like to say about them. So why don't we start with that, and then I'll go on beyond that. So, any comments about this?
I've got with me, I'll show it to you later. You're probably aware of it. And you were the editor of, I think, journal.
Who was editor?
You were one of the editors of the journal Cybernetic. I've got a 2002 edition of this thing, and that was when the Foerster died, and they had a memoriam in that.
Yeah.
I didn't know the name.
Yeah, yeah. Well, as I said, I'll start making more commentary as I go along. I just thought that you guys might have something you wanted to say about some of these slides, and maybe I will when I look at them again, but I'm not going to talk about this one just yet.
Well, it's interesting with Elion, if you look at the snake chasing its tail, he talks about the difference between historicity and prehistory, where the written, when you start writing something down, it becomes linear. And prior to that, it was all oral, and oral histories, or circular. They're not really history, they're just...
Oh, you're saying the Ouroboros is in direct contact with his beginning.
Yeah, right, yeah.
And the universe as depicted by modern science seems only in indirect contact with its beginning, which is an interesting point. I agree. Also, this thought experiment of Wheeler's is a little like the Schrodinger's cat experiment. You know, it feels like it's reducing something to an absurdity, right? It's interesting to think about that. Schrodinger's cat was, you may know Schrodinger's cat experiment, but let me say it anyway quickly. You have a cat in a closed box with a bottle of cyanide and a Geiger counter and some radioactive material, which is possibly going to decay, and the Geiger counter will detect the decay and trigger a hammer which will break the glass of cyanide and kill the cat. So from the point of view of the quantum state in this idealized experiment, there's a 50-50 chance after 1 hour of the cat being alive or dead, according to whether the decay occurs or not. So when you're doing a quantum mechanical model, you leave the system in a superposition of its possible states until a measurement is made. If the door to the room is closed, then applying strict quantum logic in that sense to the system, the cat is in a superposition of being alive and dead until you open the door. Schrödinger originally described this experiment because he felt that it was reducing to an absurdity the idea of extending the quantum model all the way up into ordinary reality. On the other hand, there are experiments which are very similar to the Schrodinger's cat experiment, so it's not obvious that, that it is such an absurdity. And Wheeler's version is really a version of the Schrodinger's cat, in that the universe is behind closed doors to that observer until the observer opens his eyes and looks at the universe. And so then the universe comes into actuality. But the observer, on the other hand, is of the universe and made of the universe. And so that changes the modality of the paradox a little bit to look at it that way. It's like you could go back to the Schrodinger's cat experiment and say, well, yes, the experimenter is also a quantum entity. And then there are variations on the Schrodinger's cat experiment, which are similar to that. So it's very interesting from a logical point of view.
Extension of this, though, is the universe itself. The universe, I hate to use the word contained, for the lack of a better word, contained within something. And you and I were talking about essentially the quote boundaries of the universe are basically process boundaries. So here's the universe as an entity, whatever the hell that is. And you say, okay, dialectically, the universe in terms of not the universe, what is it? Is it another dimension? What is it?
Yes, good question. Right.
The universe, whatever the hell that is. And so something is looking at us as the something looking at us as the universe. And so we have this something with this non-universe, not universe, the universe. And then you have this as a collection, this in terms of that. And then you keep, it's like the set of all sets.
I'm going to borrow your pad for a moment.
It's a set of all sets.
So one of the things that you're looking at is the collision. This isn't a quantum paradox anymore, it's just a classical paradox, but you're looking at the collision between classical logical thinking and the word all. Yeah. If I have a normal object like this pad, and we're thinking of it in the context of this three-dimensional space, then I could say, only slightly paradoxically, the pad is what it is not. A thing is what it is not. A thing is identical to what it is not. Well, identical, but is codetermined by what it is not. I am codetermined by everything that is not me in the space, and this pad is determined by everything that it isn't in the space. And when we now I really am going to borrow your pad, since I don't yet have that drawing pad. When I'm idealizing that and using ordinary logic, I draw Venn diagrams like this, and I say, here is the universe, a logical universe, this box, and inside this universe there is A and there is B. A is the larger one and B is the smaller one, like that, right? A Venn diagram, and then A is by assumption the inside, and not A is by assumption the outside, but obviously they completely codetermine one another in the context of that oversimplified world, and B complement determine one another just as well. So I might say, as Spencer Brown likes to say, a thing is what it is not, or a thing is codetermined by what it is not. But if you then try to put this to the whole universe, well, you can put it to the whole mathematical universe here, this little box mathematical universe. And what is it not? Well, emptiness, right? Because the complement of that universe is the empty set, emptiness. So nothing. Of course, there's another not, because you can go to a meta level with that and you can say, well, what it is not is the rest of the paper and the rest of the world. But from the point of view of the mathematical delineation that we made, what it is nothing. Its complement is nothing. It's determined by nothing. But then it's clear that you can go to that other level and say, well, it isn't really nothing. But if you went to the whole universe, imagining that you can talk about the everything, the all, way beyond the set of all sets, the everything in the entire panoply of existence, then what that is not is non-existence, nothing. And so if the universe is a thing, then it is identical with nothing. Or the complement, yeah, it's identical with its complement. But if I take that way of speaking, a thing is identical with what it is not, then the universe and nothing are codeterminate. Well, but then you don't have a story anymore, or you may have a mythological story, right? You may have a mythological story that says the universe is created from nothing, and then some story happens. Or you may not. But the limit of that goes to an apparent absurdity or an opening for a story, whichever way you want to think about it. And so this is similar to that. Let's move on. Well, for those of you who are coming in, I thought I would just go wandering through my slides for a little while up to the point where I stopped and see what themes came up or what you might want to say. But we'll probably keep to the ones that are visual. Well, I can't resist saying a word more or asking you to say a word more about compresence and coalescence. If anyone is interested in those essays by Borthoff, Borthoff spent most of his life, he passed away recently, writing very eloquently about Goethe and Goethe's philosophy. He began as a student of physics, studying with Basil Hiley, and these couple of early papers are really wonderful papers that he wrote, and I have some scans of them on my computer. So if anyone is interested in getting the Borthoff, I'd be glad to give you a link to it. I don't have the link right now, so you'll have to write on a piece of paper. Maybe you should write on a piece of paper anyway, your name and email address. I'll just pass this around. And you could mark Borthoff if you wanted it, and then I'll let you know about that. Coalescence and compresence. It's worth thinking about. Did anybody have any thoughts about it since this morning that they would like to say?
Are these intended to be hierarchical?
Intended to be
Hierarchical.
hierarchical.
You could coalesce with one object and then not coalesced object can coalesce with another.
Yeah, it could be hierarchical. It's a question of how you would structure it, right?
Yes.
Even with your glasses, you probably regard yourself as prior to your glasses, which are a mere appendage to you.
But I mean, among other things, you could put a filter of some kind, a sun filter for one thing, on those glasses. And
You could.
Either as you interacting with the coalesced object,
Right.
or a layer of two coalescences, basically.
Mm-hmm.
You're used to thinking of yourself and the glasses as one object.
Mm-hmm. Mm-hmm. And you may go back and forth between the two. Like I take off my glasses and I go into that other space,
Yes.
an interesting one where I have a little more three-dimensionality but not as much information in the particular locales. And then I put them back on, or I use reading glasses and so on. So, but you do that with your mind. You can shift from one coalescence to another in a moment by taking a different idea about things.
That
Yeah.
means that coalescence is describing the attention or our conscience, right?
Yeah.
It's a concept which describes how our attention works a little bit, right?
That's right. So a concept is like a pair of glasses, and
Goes beyond the theory into how we think about the theory and other things, how we think about things and perceive them.
exactly, right. I thought,
Interesting issue there, actually, and that is can you think about roles as
roles,
objects?
roles,
I'm playing one role here.
yeah, sure. And in role playing and therapy involving role,
People who
yeah.
have multiple
Right.
roles or obligations.
There's all those role playing kinds of therapies, right? Or acting for that matter. But if I want to understand how you think about something, I may say you're telling me that, and I try to take your point of view, right?
But if you're reading Shakespeare, Hamlet says something, it may or may not mean Shakespeare says it, but Shakespeare in the role of Hamlet.
Absolutely, right, right.
Or I could be a faculty member and a student and an administrator and a family member. And if you ask me, what do you think about this? I may have to put a hat on.
With what hat? Yeah.
Yeah.
Right.
And it will change my perception. In fact, there was an interesting experiment. I'm sure you've read about this one, in which young Japanese women who were employed were asked the same set of questions in Japanese and English, and their responses changed.
Oh, sure.
But I don't know whether it's because of the stuff war, the language constrained the answers, or the culture, the connoted culture did, or both.
Right.
But when they were asked in English, they tended to emphasize their individuality more. When they were asked in Japanese, they tended to emphasize their communal role more.
Exactly, right. That coincides with an anecdote of Feynman's that I like. Feynman said, I started to learn Japanese when I was in Japan, and then I got stuck on the following problem. I was told how to state a theorem, but if I had to state a theorem and it was your theorem, I had to state it quite differently than if it was my theorem. If it was my theorem, I had to say, I would like to tell you about my humble theorem. And if it was your theorem, I would have to say, I would like to tell you about this very great theorem. And those different evaluations were necessarily attached to the statements of the theorem.
And if you refine it still further, what you would use to describe the theorem would depend on, more closely on your relationship to the other individual.
Yeah.
Both hierarchy and knowledge,
Right.
acquaintanceship. It's
So,
very tricky.
yeah, tricky, right. And so I don't have slides for this, but I thought I would try describing it to you. Bortoft had a paper, I forgot the name of it now, on Young's experiment in any case. It's about the double slit experiment. And he attempts to analyze the double slit experiment by using these concepts. So in this way of thinking about the double slit experiment, and this is one of the ways that you know the double slit experiment, you have light or photons or electrons which are going through two slits, and then they're going to be observed by a screen. And what happens is that if you do this carefully, then you get an interference pattern on the screen, with some places giving dark bands, and other places almost nothing happens, and so on along the screen. And this is very remarkable because it happens even if only one electron at a time is going through the system. In the early days of that experiment, one couldn't so easily make complete experimental sense out of one electron at a time going through the system. But nowadays, you could look it up on the internet. You'll see that there are experiments that do that, and you can even watch the depositing of the electrons on the screen. Yeah? I think it was electrons in the Hitachi experiment. Yeah. It'd be easier with electrons, probably, to control it. But in any case, it's true in the sense of the experimentation. Bortoft wants to replace the screen with your eye, and you are looking through a glass at the source. So it's a thought experiment, but maybe it could be done too. And if you could look back to the source and see the distinction between the two slits, then there would be no interference. But if you're looking back to the source and you cannot make a distinction between the two slits, then the possibility of interference is there. This is actually correct. And he is discussing the experiment from that point of view. So in the coalescence of the observer with the experiment, when the experiment is set up in such a way that the two slits are indistinguishable from one another, then the interference can happen. It's a correct description of the experiment. The screen can't tell the difference between the two slits. The experimenter who locates an electron here on the screen cannot say that the electron came through this slit or that slit. And the usual way of describing the experiment is that if you were to put a detector at one of the slits, then the interference pattern would be destroyed. But another way of thinking about it is there really is an observer, and that observer cannot distinguish between the two slits, and so cannot distinguish between the two paths. And what is one is also two. And then he goes on, so far it's correct as far as the physics are concerned, but then he goes on to speculate that it is that paradox of the one and the two that gives rise to a vibration which turns into the interference pattern. But I've always thought that that was a lovely idea, but I don't know how to fill in mathematics that would make that actually correspond to what goes on in the experiment. But there is a principle that people use quite often in quantum mechanics, which is simply that if you have a lot of different pathways along which the particles can travel, and those pathways are indistinguishable to the observer, to the experiment, then interference is possible among those pathways. That's a correct description of what happens in the quantum mechanics, in the sense that it matches the experiment.
Isn't there literature thinking out there that interference due to speed light? I'll tell you why. If I were able to do a macro experiment, let's say with a baseball with the 2 slits, now obviously you can't make the baseball go at the speed of light. But if I were able to make the baseball go at the speed of light and had 2 big slits, I'm wondering.
You're wondering if it's the speed.
Yeah, that gives us the interference, because then we say that light traveling it does. It would be able to be at both places at the same time, but obviously not with a baseball at lower speeds.
Well, I don't know. I mean, it sounds like you would like to derive the quantum behavior from the relativistic behavior.
What would happen with a
I'll
baseball?
just leave it. I'll put a question mark on it. I don't know.
Jeremy, there's 2 things. First, the electrons aren't quite traveling at the speed of light. We find
That's right, they're not.
Yeah, but close enough.
The second thing is you look at de Broglie's matter waves, and the problem is that the wave, that there actually is a wave nature to a baseball. It's just very, very,
That's right, yeah.
very small. You'd have to have the slits closer together than half a wavelength of that object.
Yeah, I mean, the thing is that in quantum theory, everything has a wave function associated with it. It doesn't have to be moving at the speed of light. But,
So the problem is that the baseball diameter is much wider than that half frequency. So you couldn't do it with baseballs. You might be able to do it with a small amount of neutron matter, star matter.
For your fun, Jeremy, we recommend, but maybe you've read it, George Gamow's Mr. Tompkins in Wonderland, where he has a chapter about having a very large value for Planck's constant. And then Mr. Tompkins and the professor are playing billiards. But in the billiards, when the ball is hit, it turns into a wave, and because its position was very precisely determined, so its velocity is completely undetermined, and it's just a wave propagating on the billiard table, and so on, all that, right? But we're digressing. Yeah. Comments about the remarks about distinction?
Could you not have a process as an object in the presence? The process, let's say, of doing something would be of presence.
Say that again?
A process as an object being an element of presence.
Process as an object? Yes.
Dialectically. So that model would work for that, for sure.
Oh, certainly, sure. In both ways. You may be either compresent with a process or coalesced with a process. Think of the process that is you as a biological organism. You're very coalesced with it. Yeah. I probably will get back to Spencer Brown at another point in talking, but the point that I was making here is that you can look at this as making a distinction in the plane. Another mark, like some kind of little blob in the plane, would be emphasizing just that it was in the plane. But no matter what you did in the plane, any kind of indication at all would have made some sort of distinction in the plane. Each of these letters makes a distinction in the plane, either quite explicitly, like the O with its inside or its outside, or the I, where there's the black part versus the rest, and so on. We're remarkably good at playing with all sorts of phenomena of that with our eyes, of course. Yeah.
I have a question. For example, we know many examples of such loops in science. For example, such loops in formal mathematics result in Gödel theorem about incompleteness of formal mathematics.
Right.
It's a sentence I lie.
Yeah.
I lie, it's exactly this loop. and this loop result in impossibility of incompleteness,
Precisely.
completeness.
Yes, right.
The second example in algorithmics. For example, we can to create algorithm that possible to create all possible algorithms, and how this algorithm can create this self. And this
Is there an algorithm that can detect the halting of algorithms?
Universal algorithm.
Right.
I can give you many examples
I agree, yeah.
of such loops that result in the possibility of what is the result of this loop? What impossibility of what we can this loop defined? Impossibility of what?
Well, so you're asking, how is this loop analogous? Is there a loop here, and is it analogous to the Gödelian loop? The loop that there it is. The loop that I was describing here is a loop between you and what you're looking at, right? The loop that has you looking at this and understanding that it makes a distinction in the plane, so that it's not just a mark in the plane, and the distinction that it makes in the plane is something that you imagined. There are nice optical illusions that make this even more explicit, like the ones where there seems to be a triangle, but there are only 3 corner objects that create the apparent picture of the triangle. So this is a loop of perception and design between you and an apparent external world. It certainly does have the analog of all of the rest of that. For example, this in and of itself is the formal system, and you're standing outside it. But it acquires a certain property of making a distinction between inside and outside through your interaction with it. And that property is outside of what it actually does. It's incomplete. It doesn't have the rest of the boundary. You supplied the rest of the boundary yourself. So in a way, it is sort of like the Gödel theorem, where the loop is a very intimate, coalesced loop.
I completely agree with you, but it is not answer to my question.
I thought I was answering your question.
And I want to say that from this closed loop that you correctly defined and described, we can also find theorem of impossibility. It's theorem of impossibility of these things that you tell during your today lecture, because interaction between observer and observed system gives impossibility of a complete description of our system and complete prediction of our system, and it give our boundaries of using of science. Yes, our world is completely corresponded to physical laws, for example. But we cannot use these laws because we haven't complete description of our world because of this loop. And we cannot completely to use science and to predict our future, to describe our system. It's give our impossibility complete using of scientific method. And what to do? And we, in this case, we can use our intuition. For example, I don't know complete description of this world, but using my intuition, I can make correct correct movement and correct things. And I can do it because I am part of this world. I needn't scientific method for orientation in this world because I am part of this world. And it's a result of this loop. You was right that it doesn't exist full correspondence between observer and observed system. And this loop prove with its incompleteness. It's not something that I can destroy to get complete descriptions. This loop give us provement that this incompleteness of correspondence between observer and observed system is principle. It cannot be delayed completely.
Oh, I agree, but what was the question?
I think that was the question. The question is,
Oh, the,
The question was I answered my question myself.
so your question was, does this constitute a proof of an incompleteness? And it does if you look at the observer as genuinely separate from that mark. Then there's an incompleteness.
Yes.
If the observer lets go of that sense of separateness from the mark, then there's no incompleteness in that situation.
but I would argue that the incompleteness is that you can get an objective syntax, but you cannot get an objective semantics. The syntax
Well,
is
then
that.
so you made another distinction between syntax and semantics.
Yes.
Right. So all those incompletenesses involve making a certain other distinction, and then an incompleteness is seen.
Interpretation
Yeah.
is impossible without the observer, and I'd say that's the impossibility theory.
Well, yeah, I agree with that. But if the observer is coalesced with what he observes, then there isn't any question
Well,
of incompleteness.
In this particular case, but then you can always recurse.
Well, you can always make another distinction. But you see, it's delicate, right? If you're fully coalesced, then there isn't that extra distinction, or that extra distinction is just part of it. Like you're playing a piece of music, right? And you are doing it, and it is happening, and then there's no incompleteness. But as soon as you write it down and make a chart, there's an enormous incompleteness because it could be interpreted and played in many, many other ways than the way it actually is being played. And you've made a formal system, and it is separated from what can be done, and the incompleteness arises again and again in
I
this
think
kind
you
of
could
form.
even make the argument if you looked at, I mean, this gets to auto-epistemic
Yeah.
logic. Are you aware that you're aware? And that you
Well, you can always ask that question, right? So the problem, another way of phrasing this problem is one that certainly seems to get raised in Laws of Form by Spencer Brown, although I don't know that he actually discusses it directly, and that is, could you talk about a first distinction? But as soon as you try to talk about a first distinction, I could say that's the only distinction that there is, it's false. It's always false. Because in order for you to even begin to articulate something like that, you make more distinctions. Or you make a distinction between that distinction and the one that you're talking about. And this is really the source of the incompleteness, again and again, that extra distinction, which you can't avoid. So that's the way I look at it anyway.
I want to say that we cannot distinguish these two things even theoretically, because if you want to use science, you must know initial condition. If you want to
Or be willing to explore initial condition.
And to calculate your evolution, you must write with initial condition by pen. But pen, it's part of the system. You
Yes,
must
yes,
to
yes,
use
yeah.
to write initial condition with system. It's not impossible. It makes impossible scientific prediction of our evolution. It makes our incompleteness of science principally. Incompleteness of science became principle, and it's the result of this loop. It's our new modern theory on incompleteness, incompleteness of scientific method for prediction of future, and necessity of our intuition, because only intuition can use us. Intuition was not based on science, based on the fact that we are part of this world. And as part of this world, we know this world better than any science can help us.
I'd take just one last comment, back to the syntax and semantics.
Yes.
The syntax of that can be reliably communicated. You've just done it.
You mean the mark?
Yeah.
Yeah,
And most...
that's correct. I can make the mark, put it on a piece of paper, and hand it to
We
you.
understand mental processes, most people are seeing the same syntactic object or something extraordinarily
It
close.
has a certain reliability.
The semantics cannot be reliably communicated. In this case, maybe it can be, but in general, not.
We can try.
We can try, but I think that's another incompleteness.
Well, yeah.
Or lack of invariance.
Although, yeah. I mean, there is always the incompleteness of a text. I'll give you a text, but you will interpret it as you will, and if it's mathematical text, then we have to work very hard to see that we actually agree upon it. Yeah.
And you can actually come up with at least short phrases that can be read in one of two languages with different meanings.
Yeah. So.
The more fundamental incompleteness, though, comes in the very nature of induction in itself. You're referring to, let's say, a closed system. I would argue that there are no such things as closed systems. So you start off as a logician by creating what you think is a deductive system. My question is, okay, from where do you get what it is to construct that so-called closed system? And that is the incompleteness of induction. And so you have you have a semantics, which is certainly incomplete, but whatever you fill that structure in with comes from an induction.
Closed systems mean that we agreed upon some boundary conditions for what we're allowed to do and what we're not allowed to do. Part of the syntax, if you like.
Getting various interpretations of what the closed boundary is, even though you think you agree what they are, and you think.
Well, it could be geometrical. Like suppose that I tie a knot in the rope, right? And now the knot is the system I have in mind to study, and as it stands, I want to be able to move it around. But if I'm allowed to move it around, then it could disappear. So I want to make a closed system in which it could be studied, and I literally close the system by tying the ends together. And now I have a little analog, a geometrical analog of a formal system out there independent of me, as it were, because the kind of things that you can do to it without breaking it are basically the same as the kind of things that I can do without breaking it, and you can study this knot, and I can study this knot. I could hand it to you, and you play with it, and you give it back to me, and we find out that you could do various things to it, but we find out, among other things, that neither of us can untie it. And then that requires then that leads to a mathematical problem in this case, or a scientific problem in any case. How do you know that you can't untie that knot? Right. So the knot is a formal system, even though it isn't made out of little letters and some discrete set of rules for working with it.
Nevertheless, you did create some from where you got that.
So what I'm saying is that it's malleable, and it could even be destroyed. But given that we have agreed that we won't destroy it, then it has a certain existence for us that we can work with.
Still, we set the boundaries of what is.
We set the boundaries on what we're allowed to do with it. Yeah.
Which is why the Peano axioms, for instance, begin with the empty set, because a set that contains nothing on which you can do nothing is fairly easy to agree on.
Yeah, as long as you mention Peano axioms, that's an interesting thing to talk about for a moment.
There's one that's lacking. There's no axiom showing a uniformity of transition.
Peano axioms are are a good example of an axiom system for mathematics, and if I recall them correctly, they go like this. I'll use the mark as the basic symbol. So there is a symbol mark, and given x, there is the successor of x. This is like x plus 1. I'm just put a mark over a mark. I'm not using Spencer-Brown's calculus. Let me see. The successor of x is never equal to 1. And if x is, if the successor of x is equal to the successor of y, then x is not equal to y. These are all,
Equal or both not equal.
what?
They should either be both equal in there or both not equal.
Not equal. No x, if you take the successor of anybody, you never get back to 1. And, sorry. If those are not equal, then these are not equal. Thank you. So the numbers in this case are 1, 2, 3, 4, and so on. Those are the numbers. And these are some axioms about the numbers. And that will get you, there's a fifth axiom, but I won't state it.
Forever, there's a continuance.
What?
It goes on, it can go on forever.
Oh, well, I'll get to that. I mean, it didn't say you couldn't go on forever.
That's what I'm saying, it says that you can go on.
It doesn't say you can, it doesn't say you can't, but this will say something in a moment. But then there's the matter of addition. It's quite interesting how addition is defined. So x plus 1, what do you think x plus 1 is? Successor x. Yeah. And what about x plus the successor of y? Well, this should be x plus y, the successor of that. And that proceeds to define addition. I want to convince you that it does. These are the rules. These are the rules for doing arithmetic. Let's try 1 plus 1. 1 plus 1, according to the first part, is 2. Right? Put x equal to a mark. What about 1 plus 2? 1 plus 2 is, according to this, 1 plus 1 successor. But we already know 1 plus 1 is 2, and so 1 plus 2 is 3. And we just proved that 1 plus 2 is 3. And we might as well prove that 2 plus 2 is 4. That's just as easy. 2 plus 2 is equal to 2 plus 1 successor. And 2 plus 1, did we do 2 plus 1? Well, we know it from here. It's 3. And one more makes 4. So there's a little bit of arithmetic being done, right? I choose to do it this way rather than the way you might have seen it notated, so that the arithmetic actually appears out of the formalism. This is a slight difference between the usual way of writing. These axioms are usually written a little more antiseptically, and you have to work a little harder to see the arithmetic. But here, the arithmetic is just the arithmetic of these successive marks, and there it is. If you wanted to prove some bigger thing, you would have to go through many, many steps this way, you see. You could get used to doing this arithmetic, but even in ordinary arithmetic, you've abbreviated it in various ways, right? The next axiom is the induction. It says that if m is, well, actually 0 is, there is a set n. And this one says that 1 is in n. And the next one says, given x, there is a successor in n. All right? So there is some set of integers, and it's given that 1 is in n, and then the successor will be in n. So then you have to be able to talk about subsets. So if m is contained in n, and 1 belongs to m, and if x belongs to m, then its successor belongs to m, then m is equal to n. That's the principle of mathematical induction. It says that if you have 1, you know that 1 is in the set that you're interested in, and you know that whenever somebody is in it, then the next guy is in it, then it must be the whole thing. Because if 1 is in it, then the successor is 2, and 2 will be in it. And if 2 is in it, then its successor is in it, which is 3, and that'll be in it, and that'll be in it. And, and then that one is the one that is the most powerful of the axioms, because it is telling you about an infinity of things all at once. And those are the axioms for arithmetic. How many of you have seen this before? I'm just curious. Some not. But so if you haven't, and this seems a bit foreign, you see, I hope you see the point that we're saying that arithmetic looks like slash, 2 slashes, 3 slashes, 4 slashes, the most primitive kind of arithmetic. And then what are the least assumptions we could make in order to begin to get all the properties of arithmetic? But if you start here, you actually have to work a bit even to prove that A plus B is equal to B plus A. Of course, we could check that 2 plus 3 is 3 plus 2. But the proofs will be a little bit different, won't they? 2 plus 3 is equal to 2 plus 2 successor, right? And then we worked out before that this was 4, and then one more gives you 5. Then 3 plus 2 is equal to 3 plus 1 successor, which is equal to 1, 2, 3, 4 successor. And indeed, these are equal to one another. But they came about in a slightly different way. And so you have to suddenly have to be clever about something that was completely obvious to you. It's tricky. You go back, you choose axioms, and suddenly you're in a different position than you were before about the whole matter of what you were working with. And you might wonder, did I forget something? Did I really get arithmetic when I took those axioms, or have I forgotten something? Because there are many things that are in arithmetic that are going to happen quite easily that won't be easy to see from the axioms. For example, let's go back to ordinary arithmetic. 1 is equal to 1. 1 plus 3 is equal to 4. 1 plus 3 plus 5 is equal to 9. 1 plus 3 plus 5 plus 7 is equal to 16. 1 plus 3 plus 5 plus 7 plus 9 is equal to 25. This is 2 squared. This is 3 squared. This is 4 squared. And this is 5 squared. So I think you wouldn't have any trouble guessing what the sum of the odd numbers up to 11 is. 36, 6 squared. And you wouldn't have any trouble guessing that 1 plus 3 plus 5 plus and so on, all the way out to twice a number minus 1, like 2 times 3 minus 1 is 7, and 2 times 4 minus 1 is 7. You have to watch me, I can't do arithmetic. 2 times 5 minus 1 is 9. 2 times 3 minus 1 is 5. You see the numbers 1, 2, 3, 4, and 5 coming up. So this should be n squared. And how do we understand that to be true? Well, you could go all the way back to the principle of mathematical induction on the previous thing and make a proof of it by stepping up through, but you can also draw a picture. I'm sorry, I'm drawing the wrong picture in a certain sense. 1, 3, 5, you see? And 1 plus 3 plus 5 is 3 squared. And if I added 7, and 1 plus 3 plus 5 plus 7 is 4 squared. And the picture is a proof. It proves itself. It proves itself directly. You can think structurally about that, and it becomes quite clear to you that this is always going to work because you can always layer up a square in that way. So the proof is quite clear and general and works for any number n. To get to proofs like that from the axioms that we wrote is very difficult. It takes a lot of building up of language in order to get over there. And there turn out to be things that those axioms don't reach. There actually are facts about numbers that the axioms don't reach. So you need to be very careful about axioms. They might be incomplete. And you've tried to be very economical, but sometimes being very economical is not everything. But axioms have been very, very attractive ever since Euclid wrote down axioms for geometry, nonetheless. Yeah?
Just would like to comment that this proof by induction is so important because if you take some combinatorial problems, for example, have a chess board and you take away a couple of pieces.
Yeah, my favorite problem.
Can you cover this with these small pieces or not? Well, you can try to do that, and well, it does seem like it doesn't work, and you can try again, and you can try again. And that's one way, just trying.
Right.
And you can often find proof like that, and then you know you don't need to try anymore. And that is really a very big difference.
Yes.
So this is something almost magical, I think, about this way which we can actually investigate infinite number of cases.
Yes.
By this kind of analysis. So we don't need to try. We can make let the computer try, and then you can become more and more sure, but you're still not 100% sure.
Right. Let me share the problem you just mentioned.
Difference, I think, between those two
Right.
ways of thinking.
Let me share the problem you just mentioned with everyone. He's talking about a problem that you may have seen before. It's a very nice puzzle. You have a checkerboard. Let's say it's 4 by 4 to begin with. It will be even by even, but 4 by 4 is good. So I'm going to have an even by even board. And I'm going to remove 2 opposite corner squares. I think this is the problem you were mentioning, yeah? Am I mentioning the same problem you had in mind? Excuse me, sir? This is the problem you had in mind, right? Pave it. The problem is, yeah. So the problem is pave this with dominoes, and a domino, it consists of 2 squares like that, or 2 squares like that. So pave it, that's the question. Can you pave this square, this board with dominoes? Now, in this case, you'd have to explore it a bit. You try, right? You say, oh, let's see. Oops, I failed, right? Now that doesn't prove that you can't do it. That just proves that proves conclusively that I failed in that attempt. But in fact, you can't. And in a 4 by 4 board, it would take you maybe 10 minutes to convince yourself by trial and error that there's no way to do it. But in so doing, you probably wouldn't be quite systematic about it. You would, so you wouldn't really know that maybe your friend couldn't come along and solve it for you, even though you can't. But you could even list them all. If it was an 8 by 8 board, you probably had better use a computer to list them all. And you can list every possible try and find that you can't do it on an 8 by 8 board. But suppose that I said, I want you to do it on a 1024 by 1024 board. Well, then maybe that's even a little large for your computer to list all the possibilities. If not, I'll make the numbers larger because I'm claiming that you'll never be able to pave it for any even by even, whatever number you choose. And so we could easily check the present day capacities for today's digital computers and write down a number that they can't handle in this problem. On the other hand, I can be sure that it can't happen. Does anybody know why?
Yes, but I know
What?
I say yes, but I know the trick.
You know the trick, right. Someone who doesn't already know the trick. Yeah? Call it a trick, but it's actually the scientific fact beneath it. Well, every time you put down a domino, you take out 2 squares, right? How many squares are there on this board?
What's 16 minus 4?
I say, this is the easiest case. If you counted them, then
Well, let's look at this board for a moment. That may do it, but it may not, right? Let's think about that. So this is a 4x4 board. So this is 16 minus 2, which is 8, right? Yeah, now that's even, so that didn't contradict anything. What?
16 minus 2 is 14.
16 minus 2 is 14. But that didn't contradict anything. You could take out 7 pairs from 14. So that isn't good enough. On the other hand, there's another thing that checkerboards have. I'll draw it small here because I ran out of room on this one. Oh, bad. Not good drawing, but that's all right. They're often checkerboards, right? Checkerboard, right? In a checkerboard, the squares are alternately black and white. And you removed 2 white squares. But every time you put down a domino, you take out a black square and a white square. We're done, right? We're done. Because there are an unequal number of black and white squares on this board. There's 2 more black squares than there are white squares on that board. And if you were to pave it with dominoes, there would have to be an equal number of black and white squares. So it cannot be done. The proof didn't even involve induction in any strong way. It just involved the right structural observation about the situation. And we ended up proving it for an infinity of possibilities. So,
In fact, it does not even require that the 2 sides have equal length.
I'm sorry.
It doesn't require that the 2 sides have equal length. It just requires they're both even.
Yeah.
So you could do an 8x6 board and it would still work.
Yeah, you can change the numbers a bit and use the same argument, right. And you can vary the problem in some other ways, but that's another matter. You could vary the problem by removing 2 squares of the same color, of opposite colors. Suppose you removed a blue square and a white square from somewhere.
This argument alone.
Oh, then you find out you can do it. All right. That requires a little more work. But the point is that there is sometimes an enormous discrepancy between computation possibility and structural understanding. Really strikingly huge difference that can happen.
for me, the puzzle is why is that argument so strong? Everyone agrees that it must be true, that argument. But, so it's an incredibly strong argument. That's a bit mysterious, I think, to me.
I'm sorry, what was the comment again?
That this argument that we have removed 2 white spaces and domino covers 1 white and 1 black, so it's impossible. That's of course the argument.
Yes.
And that rules out everything. Then we have solved it for an infinite number of cases. And that is a bit mysterious, I think.
Yes, I think it is a bit mysterious that by such a small move you managed to solve so much. Right.
Yeah.
Right.
That's very interesting.
Yeah. Right. What I told you about the knots is quite interesting, and I thought, then there was this puzzle. Yes. Just my own curiosity. How many people think it's knotted? Nobody dares.
We're just mesmerized.
You're mesmerized?
Yes.
All right, but you agree it's a puzzle. Is it knotted or not? I have trouble seeing that it isn't knotted. It isn't. It can be undone. It can be undone. I thought I would digress for a moment, if I can make this thing work, and show you an animation of that I can create. Oop, there. Yeah, good. So here's our knot. And what I have here is a program, which is the type of program that I was investigating some time ago. But this one is written by a fellow named Rob Sherine, and it's available on the internet, so you might be interested in playing with such a program. It's called knotplot. And what it does is it does a physical experiment with the knot, a idealized physical experiment with the knot. So this knot in the computer space has been coated with electrical charge so that it self-repels. It pushes away from itself. The charge is fake, of course, so the force can be different from 1 over r squared, and it turns out that it's useful for the program to use 1 over r to the 6th. But you can adjust it to 1 over r squared. It behaves a little differently. It's just a little stronger self-repulsion this way. It works better. If it's going to repel itself and it's unknotted, then it may have enough room to just push away from itself and become a big circle. It stays the same length, but you won't probably think so when I start the program, because in the model, point to point along the computer knot are little springs. And the first thing that happens is that the springs pull in the model and tighten. So it will look like it's shortened. And then it will start self-repelling. I'm just warning you so you know approximately what goes on. And let's start it and see what happens. Well, by now you see it is unknotted, and it will take it a little while longer to untwist a bit. I'll let it run while we talk.
So this is a particular way to unknot the knot.
If it is,
But is it the only way?
Is this the only way to unknot that knot?
Right.
Oh, no, probably not. Right,
Okay.
right. Any more than if I were to,
Than the way it happened.
if I were to, sorry, I'm tangled up here. If I were to make some unknotted thing out of rope like this, there might be various ways to unknot it, and some that wouldn't work very well. Like if I pull here, it tightens up,
Right.
but it's actually unknotted, and it's better to loosen it here, and so on. But in this case, there's a uniform thing going on in that every point on the knot is trying to repel every other point, and so it pushes away from itself. And we conjecture that under generic conditions, if a knot was unknotted and it were put into a mathematical space of this kind, it would unknot. But we don't know how to prove that. We have no grasp on how to prove that.
whereas the converse,
We can do computer experiments and see it happen.
if it is a true knot, then it will not.
Oh, and I'm saying, suppose I have a knot which is unknotted, can be undone. Then it can be then I conjecture that it can be undone by this self-repelling field.
But I'm saying the other
Certainly, if it is knotted, it will simply do something, but it won't. You can watch what it will do. Let's take an example. I call this a torus knot of type 3-2 because it goes 3 times around this way to twice around the other way. And it could be drawn on the surface of a torus. The way it's living in space at the moment is kind of flat, like that, you see. Let's leave it that way so you can watch, and then we'll let the program act on it. And it's going to self-repel. There's a good example of the springs pulling in. So I can give it a little more scale. Yeah. And some color. So you see already it pulled away and got a little bit less planar, right? So because it's uniformly pushing away from itself. So you expect that it will become a more three-dimensional sort of an object, but and when it curves around itself, it tends to stay away from the thing that goes through the curve. I would like to understand what kind of geometry will a knot fall into when it does this kind of self-repulsion. Could I predict the geometry that it will fall into? But that's very hard. So this is an arena where the computer takes over at the moment. We were looking at this other situation over there where we can do much better than the computer. We can kill that problem completely, and no computer in the world could ever completely solve it by brute force. But here, by brute force, we get a lot of evidence about geometry and possible properties of this topology and geometry that we can conjecture. So it's the opposite situation. And that's the way it is in mathematics and science today, that sometimes a low-level approach like this is very fruitful, and sometimes you can go way over the top of it by making the right structural thoughts.
Three-dimensionally, which we don't quite have yet.
You're talking about the projection, yeah?
Where instead of seeing it flat, we can actually see it projected three-dimensionally at all times.
Yeah, right.
And we don't quite have that.
That's right. You're saying we don't quite have a grasp of it as a three-dimensional entity.
We don't have the technology just yet to where we can go ahead and have the three-dimensional, to where the computer can project the three-dimensional, and we can go ahead and look at it and manipulate it three-dimensionally. But
no, we have partial technologies. Like we could go to a virtual reality setup, and we could look at it in say a cave or one of the other methods of virtual reality.
In flat.
Yeah.
In a flat screen. I mean, we can go in a virtual reality, like Second Life or whatever, but it's still.
Well, you'll be doing stereo tricks or something, right? You'll be looking at it with stereo glasses. If you want to print out a three-dimensional version of it, you could, but you don't want to print out thousands of them so that you can look at.
I want to see it the way I see this bottle.
Yeah.
And I don't know, in another 15 years, I mean, Star Trek was doing the little things, and now all of us are carrying.
Yeah. It's interesting what you say, because there are aspects of human three-dimensional computation that people learned in their childhood. Maybe some of you learned these things in your childhood, and maybe you didn't, right? Because they're old cultural things, but children used to play with string, and there's a big cultural tradition about these sorts of things. And these are computations which you're doing with the help of your hands, and you find yourself learning how to produce beautiful patterns. And there's intuitions to be gained from working with that. And the computer doesn't help here. You can't get your hands on a knot with a computer the way I can get my hands on a knot by just taking a piece of string and doing cat's cradle. So it's curious. And sometimes when I'm working with a problem about knots, taking out a piece of string and working with it is better than anything else. How's this doing? Let me scale it back a little bit. That's a curious looking form for a trefoil knot. It isn't the simplest trefoil knot. Trefoil knot looks like that, but this one has kind of got two lobes which are 90 degrees to one another in space. It's stabilized there pretty much, but I can let it get perturbed a little bit and you'll see what happens. So I'm going to go to what the program labels as undamped. And undamped means that the springs are now allowed to come into use in the model. So the forces can cause the springs to jiggle. And when the springs jiggle, some of the energy gets thrown into kinetic energy due to the movement of the springs. That causes perturbations, and we'll see what happens. I let it run for a long time, so the perturbation takes a correspondingly long time. It's sort of beating its way slowly up out of a potential well. I couldn't write down the analytics of this, but what will happen is that it's going into an unstable oscillation. You'll see in a moment what happens. No. A natural energy to define for a configuration like this is the sum of, if it were the ordinary 1 over r squared force, would be the sum of the potentials between pairs of points on the knot, the sum of 1 over r all the way around the knot. The computer program calculates that, and this has an energy, which is now varying a bit. Let me see if I can find the energy button. There goes. I won't worry about the energy. It's now falling down into a lower energy level. And more kinetic energy is going into the springs. And that lower energy level has a different geometrical shape than the higher energy level that you saw. And if we now undamp it, it will fall into a somewhat more rigid form, and you'll be able to see it. Looking a little more like the simple trefoil knot that you might have thought of when I said trefoil knot. The 3 lobes more or less symmetrical with respect to one another. The lowest energy level of the knot from this point of view. So this is just to show that you can do all sorts of physical experiments with knots inside a computer, quote, physical experiments with knots inside a computer, and I thought it would intrigue you. later, when we're done, are we near the time when we have to stop? We can keep going. Okay. Yeah. So it was unknotted. Maybe I should have played It's Unknotting for you one more time, but I don't find it easy to visualize how it got unknotted, even after having seen the demonstration. But if you were to copy it carefully with a piece of rope, the rope would fall apart very easily. So there's something to think about. That's why it's a deep mathematical subject to study knots. It's just not at all obvious when they're knotted and when they're unknotted. Yeah.
It's kind of a cognitive dissonance because of it being an optical illusion. No, you don't see that?
Oh, I guarantee you it wasn't an optical illusion that this thing really did get unknotted. Yeah.
No,
but
I know that. I'm talking about, for me, looking at this right now,
yeah.
it is an optical illusion because of that
Oh.
far right-hand side. You see?
Yeah.
How it curves around and is connected.
It's a little hard to see what it did
All right, so
under there.
You take your pointer and go down.
Yeah.
Now over to the right.
But if I said to you,
Actually, to me, looks like an ending.
yeah,
Okay, as opposed to
Right.
looping around and back.
right. I
That's why
don't.
When you asked the question about knotted or not,
Yeah.
I would have had the inclination to say.
You would have had to ask me, well, how is it connected up back there in the shadow? Right. But if we had decided to make it, then we get into the awkwardness of weaving it. It is a bit awkward. I can try. It's usually better on a flat table to make a weave than it will be here. I think I'd better not try. But you see what I mean. You could try. But I agree. Maybe if I use this again, I will try to get a better shot so that you can see clearly what happened there. Right.
You can see the upper right hand was kind of pushing down and starting
Yeah.
to fold. The one behind.
If you remember what happened, you remember that this part here started sliding down, but it's still not so easy to see. That difficulty in seeing whether something is unknotted is exploited by magicians. For example, a well-known magic trick is to make a square knot with a lower loop, like that, and then thread through the bottom like that. This is a more complicated knot. And then to make an apparently even more complicated knot by threading one more time and getting out of the way, and then you find that it's unknotted. This one also is a bit mysterious, even though you can make it by hand and watch it unknot.
Could you do that just like 20 or 30 more times?
Let's continue. There was the DNA. Comments about the DNA?
What is the significance of knotting in natural phenomena? What does it do?
Yeah. In the case of the DNA, it's very significant. The fact that DNA can become knotted is related to the fact that it can become unknotted. And it's related to how DNA reproduces. So let's go back and talk about that for a moment. How does DNA reproduce? DNA becomes two DNAs, according to the scheme of Watson and Crick. In the scheme of Watson and Crick, the DNA is understood to be a double helix made of a sequence of bases and another sequence of bases, and they're paired together in bonds across, and when the DNA, and they are wound, helically wound around one another. So they're linked many times around one another, like this red rope and this blue rope could be linked around one another many times, like this. So the DNA looks like that, this segment, like that. And then the story about the reproduction of DNA is that the strands come apart under the action of certain enzymes, polymerase enzymes, and then when a strand is all by itself, the bond's broken, then the environment consists of all those base pairs, and there are other enzymes which sew the complementary enzymes back onto the bare strands. And what would you have after all that had happened, if that was all that had happened? You would have two highly interwound copies of DNA, linked many times with one another, around and around and around. That unlinking has to be gotten rid of, and it might be gotten rid of by spin them or pull them apart like this, like I can undo that, but there isn't anybody's hand that can reach into the cell and spin them apart. So people discovered in the late 1970s, Wang and his group at Harvard, they discovered that there is another class of enzymes which proceed to do the unlinking somehow, but the local action of those enzymes is to switch crossings, so that if the DNA is crossed over with itself like this, the enzyme can break this apart into two, slide this through, and then come back together. So it would be something like this if I use the ends of the rope to illustrate it here. Here is this, which is in front of that, and the blue rope is linked with the red rope. The enzyme comes along, breaks this, allows the red rope to come through, and unlinks it from the blue rope. So the enzymes have to do this in some multifold way, many, many times, in order for the two linked strands of the DNA to come apart. That means that these same enzymes could cause DNA to get knotted up with itself. So the same things that can make it simpler can also make it more complicated. And so one of the proofs of the actions of those enzymes were these kind of micrographs which proved that DNA could become knotted. But if the DNA were to become knotted and not get unknotted, you'd be in big trouble. Then mitosis wouldn't work, the cells wouldn't divide, and the animal would die. So that's the story. There's a lot of topology being orchestrated down there, and people don't know everything about it, or actually much about it. The other, this could be identified, this is a table of knots. This is the first knot, a knot, and this is the next simplest knot, and so on, and a tabulation up to 8 crossings in this case. And this knot here is one of them, and you might look for it on the table. If you rotated the picture by 90 degrees, or was it 180 degrees? What did I do? I rotated it by 180 degrees so that this part down here is up there. And then I think you can find it on the table. Can you find it? Look for this on the table. Well, let's see, it's got, how many crossings does it have? 1, 2, 3, 4, 5, 6, 6 crossings. And of the 6 crossing knots on the table, there's 6-1, 6-2, and 6-3. There are only 3 of them. So, must be one of those.
Looks like 6-2 maybe.
Which one? At this point, you have to think like a topologist. A topologist is somebody who doesn't know the difference between a donut and a coffee cup. You have to be willing to deform the picture you're looking at here in order to get it to match one of these. It's not going to be a perfect match, but structurally it'll be a match. It's 6-2. You see that loop at the bottom? There's the loop at the bottom. It's bigger here. Over, under, over. And then there's two little weavings up at the top. There they are here. So it's pretty clearly 6-2. And then there are optical things, like you have to be willing to understand that this strand goes under, and then it goes over. And this strand is going over that way, and this one is going under. I'm told that the biologists who make these micrographs have to throw away a lot of them, and they agree on the ones that are readable. I mean, a lot of them are not readable. This one is readable, but you have to do some interpreting, right? When you're down in here, that this is over and that one's under, and that this crosses this way, right? And this crosses under. Take some interpretation. Syntax and semantics again.
That could be determined by laser tracking, I would think.
These experiments are hard to perform. I suppose in future they'll become easier and the pictures will become better. Yeah.
It's like they do laser tracking around.
But the problem is you have to worry about destroying what you're looking at.
Yeah. You did have to destroy what you were looking at. That was the basis of this technique, was to coat the DNA with protein in such a way that it became big and fat so that you could look at its geometry. Yeah. Anyway, I wanted to make one more remark about the DNA knotting. This is a fascinating thing. That's just our picture again, and this is a thought experiment, but it actually was one that was carried out. Suppose you had a DNA that was not knotted, just twisted up. I have trouble with where did that go? There it is. It's got a little twist in it, that's all. And that's natural that it would have some twist in it. That's what happens to your phone card, and it happens to DNA as well. And then there's a recombination that goes on. It comes near itself here, and there's an enzyme, a recombinant enzyme, which cuts it apart and puts it back together, crossed over, like I've indicated in the next picture below. Right there. So it cut it apart here and put it back together, taking the left strand to the right one and the right one to the left one. That form of cutting apart and putting back together is called recombination, but it might have done it with a right-handed twist, or it might have done it with a left-handed twist. Which did it do? In the thought experiment, I have it doing it with a right-handed twist. Does the enzyme consistently do it with a right-handed twist? How would you know? Well, in the thought experiment, I could find out by watching the products. I make it do a recombination, and then I make it do another recombination between two nearby points, and then I make it do another recombination and yet another. And I would get these products coming out. And then I could look at their topology. This one simplifies. It's two linked components. This really is two components. And this one is a simpler knot, like that. And this one is two components. And that one's another knot. That's in the thought experiment. But then that's a prediction. If it does a right-hand twist consistently, then when you do the photomicrographs of the results of this experiment, you should see these knots and links. And if it was doing a left-handed twist, you would see a different set. And if it was doing a random thing, you'd see things from all sorts of different things. So what does happen? Well, they did the experiment in the case of this particular kind of DNA, and they found that they got this sequence of knots, maybe up to the third one, not all of them, they wouldn't see all of them. And so that confirms that it does recombination with a particular handedness. So in this case, the topology became a kind of a way of magnifying something that you couldn't see otherwise at all, the handedness of the way the enzyme behaved, because that handedness then affected the global structure of the DNA and became something that you could see. A genuine microscopic application of topology. Comments? I couldn't resist saying a little more about it because it's such a nice piece of science. Due to Stasiak and Spengler and someone else whose name slips my mind, back in the 80s actually, and people continue to do this sort of thing. There's the dolphin. I thought you might want to see the knotted vortex film again, so I'll do it again. I think they have better ones on the internet now. You can look them up.
Is there a handedness in this, a chirality in these?
Well, yeah, this, of course, is Cairo. They deliberately made a trefoil of a given handedness, right-handed trefoil, but they could have made a left-handed trefoil just as easily with that apparatus. And in principle, any knot at all could be made into a knotted vortex by that method, but it probably gets dicey and needs better and better equipment as the knots get more and more complex.
Does the chirality of the DNA follow that of a water molecule?
Say that again?
The chirality of DNA follows that of the water molecule. The water molecule is chiral too.
You're talking about the basic helicity chirality of the DNA. Yeah. I'm not sure. I don't know about the chemistry of that. I'd have to look it up.
What I wonder at that point is whether or not, let's say, the chirality of the water molecule, which I think is right-handed, then transmit that structure, transmits itself all up the line. Somewhat kind of like somewhat analogous to the Coriolis.
Yeah, good question, but I don't know anything about it, unfortunately. So let's see now. This is where I stopped. How much more time do we have? We have 1 hour, and it's time for a break, isn't it? No? It's okay? I guess your thing goes longer than I thought. Let me stop for a moment and think about what in these slides would be good to do next. I'm going to probably skip around in this way because otherwise it's less flexible. But this is another mathematical exercise that I think is intriguing, and you might have seen it before. Another puzzle. This one is about the cybernetics of description, but you might not suspect that from the form of the puzzle. I give you the puzzle bare. Here's a sequence of numbers, 1, 11, 21, 1,211, and so on. And what's the next number in the sequence? Well, I'm not going to torture you with this.
Thank you.
But it's actually quite a bit of fun. How many people know this puzzle? Okay, good. It's quite a bit of fun to torture mathematicians with this puzzle because mathematicians, as say opposed to logicians, who might know about this kind of thing, are very likely to work very hard at it and never get anywhere. But before I go to the next slide, if you would speak it out loud, then you will get a hint. So I shall speak out loud. 1, 1, 1, 2 ones, 1, 2, 1, 1. Where's my 1, 1, 1, 2, 2 ones, 3 ones, 1, 2, 2 twos, 1, 1. So each number is, when read aloud, becomes a description of the previous number. So this is the cybernetic. It's a cybernetic exercise, which could be called describing, right? You start with almost nothing, 1, and start describing it, and a complex structure arises. I could start with a star instead of a 1, and then I would say 1 star, and then I would say 1, 1, 1 star, and then I would say 3 ones, 1 star, and then I would say 1, 3, 2 ones, 1 star. And it would go on and on like this. John Conway investigated this, and he found all sorts of interesting theorems and theorems about the limit numbers, and you can look it up on the internet if you like. I don't intend it as a detailed mathematical exercise, but more as an illustration of the creation from nothing in a cybernetic or recursive way. It's quite amazing to think on this. And you will notice some patterns, at least. There are some surface patterns. If you go down by 3, 1, 2, 3, you see that what you have here is extended. And again by 3. 1, 1, 3, 1, 2, 2, 1, 1, 1, 1, 3, 1, 2, 2, 1, 1, and then it continues on like that. And this is true in general, that whenever you go down by 3, you get an extension of what you had before. And that means that if you kind of wrapped it all up together like this, then you would find that B describes A, 3 ones, 1, 1, 1, 3, and so on. And C describes B, and A, the one that was 3 above, describes C. So you end up with 3 infinite sequences of 1s, 2s, and 3s, which describe each other circularly, like that. A kind of mystic circle. And I've drawn in the middle of it a Borromean rings, which is a link, which is only linked because all 3 of them are there. Right? One of them, let's see, from the view you're looking at, which is a little poor, green is over red, green surrounds red, red surrounds blue, but blue surrounds green. There, just like the triangle. And of course you have to use more topology to actually prove that those links are linked, but they are. And this complex structure is coming out of nothing but describing. And you don't even have to start with a number, right? You just start with star. It's worth thinking about. There's the Borromean rings in a little more vivid incarnation. And here's a quote from Spencer Brown about the same subject. I haven't talked about eigenforms directly. Maybe I should. I'll try this. Let's talk about what is the reflexive domain. This is a little more abstract, but maybe not so abstract. I want to talk about the kind of domain in which second-order science should occur. So that's a domain in which every participant is also an actor. That I may be involved in the market, but I'm also putting forth ideas about the market. I may be buying goods, but I'm also selling them. I'm trying to think up a theorem and send it to you, but I'm also reading your theorem. It's all reciprocal in that way. And I would like to say it in the most general way I possibly could. So I have a domain in which there are persons, actors, elements. I say space, but the points in the space are you and me and whoever is involved. They're the objects, but they're also transformations. So every point in the space is also a transformation of the space, and every transformation of the space should also correspond to a point in the space. It's a little abstract, but I want to explore it. If you want a mathematical example, they are easy to come by, almost easy to come by. Think of the complex numbers, right? A nice geometrical domain of rotations. And every number in the plane is also somebody that you can multiply by. And when you multiply a complex number by a complex number, that number gets rotated by some angle and stretched by some amount and ends up somewhere else in the plane. So rotation and stretch is the kind of transformation I have in mind for the plane. And every rotation and stretch corresponds to a specific number in the plane, and every number in the plane corresponds to a rotation and a stretch. Okay? So that's a reflexive domain. And I'd like to know, how do reflexive domains behave? So, as I said, this is just saying the same thing again. The reflexive domain corresponds to its own mappings to itself, which is what that means, mappings from the domain to itself. Probably don't need to say that. But then, I do allow things to act on themselves. If I have an object in the reflexive domain, then it could act on itself, and it could produce a new object. In the case of complex numbers, a number can multiply itself. Like I can multiply itself and give you -1, or 3 squared is 9. So things can act on themselves. And then I will prove a theorem. I'll prove to you that every transformation of the domain has a fixed point. And the proof is too simple. The proof is, I'm going to define, I'll write it on the board because it's too simple. It goes right past you. It's sort of like the solution to the checkerboard problem. Too simple. I define a new transformation G by G applied to X is equal to T applied to X applied to itself. So that means that if I took G and I applied it to somebody standing there, then I would get T applied to that person standing there acting on himself, like that. But what happens if I apply G to G? Well, then I get T of G applied to G. And you see that G applied to G is a fixed point of T. Now, there's another way of saying this sort of thing, the existence of fixed points. Let me give you an example. Suppose I define box of X to be equal to a box around X, right? And I say there's a fixed point for that. There's a form which is fixed by box. And I can approximate it by applying box again and again. So if I apply box to X, then I will get a box around X. And I could keep on going in this way, and I could invent a super box, which was an infinite nest of boxes. And then if I put one more box around the super box, I get it back. Because putting one more box around the infinite nest of boxes Didn't change it, just shifted everybody down by one, and we ended up with infinitely many. So I went outside the original domain. I jumped to an infinite domain and went outside the original domain and solved the problem, right? It's an old joke among mathematicians to form this structure, which is sometimes called Hilbert's Hotel in another incarnation. You have a hotel, and it has infinitely many rooms, labeled 1, 2, 3, 4, 5, and so on. And the manager is very proud of this hotel because he advertises that there's always room for more. So for example, if the hotel is full, and I come to the hotel to the desk and I say I want a room, they say fine, and they notify all the guests that they have to move up one room. Well, the advertising didn't say it was going to be convenient. Now room 1 is empty, and I occupy room 1 and I'm done. I'm in, right? And a football team with infinitely many people come to the hotel and they want rooms, and the manager says, fine, put everyone in room N into room 2N. And now all the odd rooms are empty, and they put the football team into the odd rooms. So it's the same idea. And there's a fixed point, but we went outside the domain.
Isn't that what Cantor did, though, basically?
What?
Isn't that what Cantor did in the preceding sets?
I'm sorry?
In Cantor set theory, basically you just add another set.
Oh, well, it's related to set theoretic paradoxes, but I'd have to change my language to bring it up. So, yeah. But then what happened with the other way of looking at it? I said G applied to X would be equal to a box around X. I'll use a different box, half box, but it's just a box around X. But I'm not going to do that. I'm going to do this, where it acts on itself, all right? Now, this seems like a perfectly normal enough operator as far as most things are concerned. For example, G applied to an ordinary square box would be 2 square boxes surrounded by a curved box. It's only singular when you try to apply G to itself. You thought it was all right to apply X to itself, and it is, but you went outside the domain when you applied G to itself. That's where you went outside the domain. You had to go outside the domain in either case. This time, we applied G to itself, and we got GG inside here, and so that looks like a fixed point for box, right, in there. Where did we go outside the domain? In applying G to itself. You see, G isn't a number anymore. If it was the complex numbers, it becomes perfectly clear, right? Things are complex numbers. You could multiply them by themselves. But the operation G isn't any longer a complex number. So you have to be very careful. You would like to have a reflexive domain in which you could do this. And so you can build, but in order to do so, you really build language. This is where language builds something that can become useful or real. In the language, I can do this operation and get a fixed point. And I didn't have to do infinitely many things. I just got a formal fixed point in the language. There it is, GG. And that has the property that it acts like it had a fixed point, and it can be the pivot or source of the recursion that's involved. GG being substitutable for GG with a box around it, could be substitutable for GG with 2 boxes around it, 3, 4. If it's not a box, it could be something else. And this turns out to be the basis for many computer language recursions, this move in language, which is due to Church and Curry in the 1930s, called lambda calculus in their terminology. So eigenforms are fixed points in the most general sense of being able to form the fixed point of an arbitrary transformation. Some fixed points that you try to make in mathematics are themselves in the original domain. Like if I'm talking about real numbers, then, and I want a number so that, suppose I wanted a fixed point for, I'm making one up, tau of x is equal to 1 plus 1 over x, all right? And I want a fixed point for that. Well, that turns out to be the golden ratio, 1 plus the square root of 5 over 2. There's a fixed point for that. It doesn't change under that. So it's still a real number. But on the other hand, some equations don't have real number solutions, and then you had to go outside the domain, like f of x is equal to minus 1 over x. That's a nice transformation of numbers, but if you had a fixed point, it would be x equals minus 1 over x. That would be x squared equals minus 1. It would be I, but it would be a complex number, not a real plus or minus. Being not a real number, complex number. You went outside the domain of real numbers. In general, you can always have a fixed point, but you'll go outside the original domain. If you had the ideal reflexive domain, you wouldn't go outside the domain because the operators and the operands are equal to one another. So that's what happened here. In the reflexive domain, everybody has a fixed point, and it's still in the domain by definition. But to make such domains, you have to have an ever-expanding language. That's the only practical way we ever do it. We do it by ever-expanding computer languages where you can keep on defining new macros in the language, new functions, new programs. If you try to make it absolute, it usually breaks.
In your binary system, each of those 16 functions is a result of an operation as well as an operator.
Yeah. Yeah.
Simply a reflexive.
Yeah, that level of reflexivity is always happening in algebraic or numerical systems, right? That things take both roles, like the famous equation 3 times 3 equals 9 says 3 threes is 9, and one of the threes is an operator which triplicates the other 3, which is an operand. Which one is which is your interpretation. Right. But this double level, you see it's such a simple proof that and there's too much to talk about, right? This double level of duplication is tame, but defining somebody which involves the duplication and hoping that that somebody is still in your original domain is too much to hope for in most practical cases. You'll be propelled out through a singularity into a new domain. The other thing about fixed points is a very common mathematical point which you don't think about very often. It has to do with convergence and limits. Think of a real number, like the square root of 2. A very definite real number. Yeah? Definite from the point of view of geometry, it's the diagonal of a square. But not at all definite from the point of view of its decimal expansion, which you only know up to 4 decimal places unless you're very special or have a computer at hand. Right, 1.414, something. But it goes on forever. And it goes on forever and indeterminately unless you have the algorithm available. You can't tell me what the 10,000th digit of the square root of 2 is without the algorithm. There's no way to know without computing it. So in what sense is it a definite number? Well, only in the sense that all of those approximations are getting closer and closer to one another. You have a bunch of numbers as you keep expanding the decimal, and they're all getting closer and closer to each other as they go farther and farther out. And that's what we call a convergent sequence. And we came after thousands of years to call such varying processes definite numbers. Not definite in that they're completely known, but definite in that they don't go out beyond the error bounds that we set as we set more and more restrictive error bounds on the numbers. And that's what real numbers are that you use all the time. So they all go outside the system of the Greeks. That's what I'm saying. The Greeks wouldn't have been happy with any of that. They would have regarded all of those as ideal as these. Yeah.
I wonder if you look at these not as numbers, though, but as processes. Like, for example, pi and stuff like that. These are not really numbers, really. Because again, we get into that business of a limit. You know, you may use a limit.
Well, there you go again, right? I mean, there we go again. It's the same thing. Pi, as a decimal, is 3.14159, and it goes on forever.
But it's not really a number.
Well, but that's what I mean. That's what I was saying. Should you call it a number or not? It's the ratio of the circumference to the diameter of the circle, and we want to call it a number, and so we have decided since Plato to extend the language in such a way that we call it a number. I could iterate the same complaint about that as I was complaining to you about people talking about fields when I don't think they should call things fields, but I give up as far as not calling that a number, in as much as ever since I was a little child, people have been calling that a number, and that's just a small span of time during which it's been called a number, right? Can we stop them from calling it a number? It would be better to call it a process, the pi process, right?
The same thing that I
The only problem with calling it the pi process is that it shows up so many different ways.
Yeah, exactly. If you call it a process, then you want to say which process, and there are lots of different ways to get to it.
process in a different form expressed differently.
Like you see, one of my favorite pi processes is this equation.
I think you're using that's an amphibole.
Viet's formula from the 1500s for pi, where each time you take the 1/2 plus 1/2 the square root that's in the previous one, and it's an infinite product below, a limit. That's an excellent little algorithm for computing pi. You just keep doing that over and over again, dividing. The denominator factors are going to 1. It converges to pi. So it's been useful conceptually to call them numbers. I have no real objection to it myself.
What you're doing is, the problem is not a process, it's a class of processes. It's a class of processes. There are a number of different formulas, there are a number of different statistical simulations that all involve pi, from which I can isolate pi. We can prove they result in the same number, but they are not the same process. They have nothing to do in some ways with one another.
Yeah, and with pi, it's been studied in so many ways. There are many processes, like there are probability problems where you toss a ruler down on a striped a table, and pi will come out. Or for that matter, pi comes out in relation to the standard normal distribution, and in many other ways. So you probably don't want to limit which processes you're aiming at when you talk about pi.
Right, that's my point.
Yeah. Okay.
Isn't an infinite division a process in itself?
I'm sorry?
It is an infinite division a process in itself, though it's not really. For example, 22 over 7.
So along with there being an infinity of digits, there's actually an infinity of processes that somebody could decide that I want to discriminate between them. Yeah. But you may have your favorite one. Let's go on a little bit. There's the summary again. And here's the duplicating mark, as I said before. Of course, this notion of of re-entering can be very geometrical. It's worth looking at a couple of examples, but we all know these examples, I think. Here's the mark, and what I'm doing is I'm re-entering the mark into itself, but not in the usual way of putting it underneath. I'm taking an edge and I'm putting a 90-degree bend in place of the edge. So you see, here was the mark, it disappeared. And a 90-degree bend and another 90-degree bend appeared. And then for each of these 90-degree bends, I put in a 90-degree bend. And again, an ad infinitum, and you end up with a form which is self-similar to itself and actually superimposed with itself, going around like that, and then superimposed around like that. Two copies at 90 degrees to one another and overlapping. Fractal. And the Koch curve is a good example of the same sort of thing, where in this case I have two sides of a 60-degree equilateral triangle, and I replace each edge by that again in the 1/3 place. So I take the middle third and replace it by the triangle, and I do it again and again and again, and we get the Koch curve and all the things about fractals that I won't mention. So I wanted to talk about a relative of that G. So this is an abstract version of what I call the indicative shift. But I want to fill it in for you a little bit. The filling in is in this dark box here. I'm thinking of a name referring to an object, like my name referring to Stu. And if I haven't met him, then the name is over here. Somebody told me it was Stu, and there's this person over there. But if I'm any good at learning people's names, then the next time I see him, he's Stu, and Stu is over there cognitively with him in the space for me. So the name is projected to the object, just as the chairs are chairs, and the projector is a projector, and so on and so on. And we do this all the time. This taking of a piece of language and putting it into an object in the world so that it adheres to it for us cognitively. Rope is a rope on the table. And if that isn't happening with you, then you get nervous, like you can't remember somebody's name whom you know, or maybe you walk into your apartment and you don't recognize anything and you don't know the names of those things. Well, you'd be worried, right? Because that is part of your normal operation all the time of doing that, and qualities. So that's a shift. You go from the name pointing to the object to another condition, which I call metaname, and then the object and the name are together. So metaname A is pointing to B with A attached. A points to B, metaname of A points to B with A attached. It's a standard operation. You could look at it in the most simple case where nothing points to nothing, but then the metaname of nothing points to nothing as well, because you shifted nothing. So the metaname of nothing is the name of nothing. And the metaname of nothing is the metaname of nothing. But the metaname of the metaname of the metaname of nothing is the metaname of the metaname of the metaname of nothing. And you arrived at a self-reference at the third departure. A simpler, I didn't go to a simpler version, so I better do it. Are we near the end of time? Okay, so we'll finish this and stop. Suppose that I have a name for the metaname. Everything has a name, so the metanaming operator, that shifting operator, it should have a name. And then what happens when you shift that? Well, the metaname of the name of the metaname is the metaname of the name of the metaname. And you get self-reference. That's a very algebraic way of saying the same thing that Heinz said. I am the observed link between myself and observing myself. It's not different, really. But I think it partly answers the question, why don't we keep on recursing forever? Why don't we keep on falling into the name of the name of the name of the name of the name? Because somehow we're built to stabilize that self-reference that naturally occurs. I don't know how exactly. If you're programming a computer and you don't want it to keep on recursing, you tell it to stop at a certain point. Here, it has to do with the way it fits back into itself.
I like that from a halting problem.
Say that again?
Relate that to a halting problem.
Halting problem? Yeah, but in this case, it's not that you're trying to solve the halting problem by figuring out whether something halts. You're trying to, you in fact naturally stop at a certain point. You don't go beyond this place of where it comes back. Maybe somebody does, but it would be pathological. So I want to make one more comment as long as we're at this point. The pattern is the same as the Gödelian shift. So indeed, getting back to what he was remarking when we got to the mark, we're looking at the same circularity with different levels of amplification. What happened here is that I have a G, which is the name of, or the number of, a statement which says there is no proof of the shift of whatever you put in there. That's what it says. There is no proof of the shift of whatever you put in there. B stands for device, proof. There is no proof of whatever you put in there. But if you shift it, you see that now sharp G, metaname G, refers to there is no proof of whatever sharp G refers to. So this fellow on the right says, I have no proof. That's what it says. And if there's a naming system, and that's what Gödel devised, a naming system using numbers, then you can make statements that say that they are unprovable within a system.
We have to move on to the next session.
Yeah.